Okay, so what will we get if we take secant squared of x minus 1 and we plug it in for tan squared of x right here? Well, this is what we're going to get. Our next step, so we're back to our original thread, our original chain of equal signs. We've got secant of x, and it's going to be multiplied by tan of x plus secant squared of x minus 1. That was what we plugged in for tan squared of x. And then we still have minus secant squared of x inside the brackets, and then all of this, as before, is divided by 1 plus tan of x all squared. Okay, well now you can hopefully see what's going to happen. We've got secant squared of x. Yeah, these brackets I put here just to make it clear that this was the expression that was plugged in for tan squared of x, but these two brackets that are around the secant squared of x minus 1, they actually don't do anything, so we don't need to, there's no concern, right? There's an addition outside, so they're really just there for looks, for cosmetic purposes. So we've got plus secant squared of x, that's going to cancel with the minus secant squared of x over here, and that's why this works out so nicely, because now what we have is secant of x times tan of x, and all that's left is the minus 1 now, so tan of x minus 1, and now this is starting to look a little bit more approachable. So this is our f prime of x, right? Let's just to really quickly just go back and remind ourselves of the context. So we were working out f prime of x, we did all these calculations, we used this limit identity to do a substitution, and we ended up getting this as our derivative. So when is this equal to 0? So let's answer that question. So f prime of x is going to equal 0, well, when the numerator is equal to 0. Right? That's when fractions are equal to 0, when the numerator is equal to 0, provided that the denominator isn't also equal to 0. But what we have here is a numerator that's multiplied. It's a secant of x times tan of x minus 1. So the numerator is going to be equal to 0 when one of those two factors is equal to 0, right? When either secant of x is equal to 0 or tan of x minus 1 is equal to 0. It's going to be one of those two equations that is going to be, the only way the numerator is going to be equal to 0 is if either this equation is true or this equation is true. That's how we can break this down even more. So now the first thing you might notice is that secant of x is never equal to 0. This never happens. And why is that? Well, because secant of x, remember, is equal to 1 over cosine of x. And when is a fraction equal to 0? When its numerator is equal to 0. But this numerator is always equal to 1. So secant of x is never going to be equal to 0. So you can rule this one out and forget about it. Really, we're just going to it's going to come down to this equation. So finally, we want to solve when is tan of x minus 1 equal to 0. That's how we're going to get our values that give us horizontal tangent lines. So you can solve this equation. When is tan of x equal to 1? Well, that happens, well, draw your trig table, and you can get one of the values that way. Or you can use special triangles, use whatever method you like, but you're going to end up getting the value x equals pi over 4. Let's just draw, since we got the space here, let's just draw a quick picture of the graph of tan. Remember, its fundamental wave looks something like this, right? It's got a vertical asymptote at pi over 2 and at negative pi over 2, and in fact, at any multiple of it'll have a vertical asymptote at pi over 2 plus any multiple of pi, because it's got a period of pi. So this is the fundamental wave, but it also repeats out here, right? It's going to have this sort of behavior, and it just repeats on and on in either direction. So it's going to draw one part of a wave over here as well. I won't draw every single asymptote, but what we have here, if I were to draw the number 1 there on the y-axis, what we really have found is one solution to this equation, to tan of x is equal to 1. This is one place where it happens, but there's other places where it happens as well. And in fact, if I want to get the other places where this happens, I can just take pi over 4 and add any multiple of pi. And I will get all the other places where tan of x is equal to 1. So in general, what I can say, if I want to make sure I get all the solutions, I don't want to just say x is equal to pi over 4. I want to say x is equal to pi over 4 plus n times pi, where n is any integer. Remember the integers are the positive whole numbers, like so +1, +2, +3, 0, -1, -2, -3. So those are going to be the values where tan of x is equal to 1. Or in other words, when tan of x minus 1 is equal to 0. Or in other words, when this fraction is equal to 0, because that's what's going to make this expression over here 0 and thus make the whole expression 0. But this was f prime of x, right? So we're just tracing back our logic to recover the context that we're working in. In other words, we found all the places where f prime of x is going to equal 0. And to go back to the context of the original problem, we found all the values of x such that the tangent line to the graph of f at the point x is horizontal. So that's what we found here. So these are the values. And really, we can just draw, we can either repeat everything we just said now in a fresh line at the bottom, or why don't we just draw a box around here, because these are really all the solutions. We've captured them all. Okay, so that's how you can solve a problem like that.